In this video, we're going to discuss repeated measures analysis of variance using a technique of fitting the model called maximum likelihood. This model, we use proc mixed in SPSS, and this particular methodology of doing statistics gives us a much broader way of fitting models of repeated measures. Repeated measures addresses the problem of lack of independence between observations. And there are many ways that you can address this lack of independence. So to see an example of this, let's go back to our longitudinal vision data file, and we're going to concentrate on myopia patients or subjects and look at their development over the years before and after the onset of myopia. And so that's going to be this variable init years. So let's look at analyze mixed models, linear. And now on this first page, we have to identify the subjects, a subject variable, and a repeated measures variable. Now, one thing you should notice in least squares ANOVA, the kind we use with the statistical package of SPSS, General Linear Model, the data was organized horizontally. There was an AL 0, 1, 2, 3, 4, 5. In this case, years goes down. It's a vertical arrangement of the data. And so the repeated variable is just one measure. It's not 6 like in the general linear models that we did with the Chow data. So the other thing that is most useful with this model with respect to the repeated measures is that the data do not have to be complete. In other words, there can be missing data. In the general least squares model, when the data is lined up horizontally, any missing data, any year that's missing, or any repeated variable that's missing, results in the entire subject being dropped. The other thing is you need to look at the covariance type of relationship. So this is the correlation between the observations, the repeated observations, the lack of independence. There's quite a few different models that we can choose from to address this. In the repeated measures of the general linear model, the greenhouse geyser and Hunfeld all go to kind of make an adjustment assuming compound symmetry, or that there is one common correlation coefficient between all the different variables. All right, once we have selected our covariance type, then we go into the next step. And we have to pick an independent variable. We'll just use refractive error. And the factors, let's say we're going to have a fixed factor of ethnicity. And we're going to treat years prior to or relative to onset as a fixed factor as well. Factors up here are categorical in nature. Now you could consider years before and after as continuous and put it down here with covariance. But that would assume a linear relationship. We don't necessarily believe, in fact we've seen that it's not really completely linear. So we're going to go with this. Now you have to specify your model. And our model is going to be the full factorial, which is ethnicity by init years. It's going to be the factorial, which gives us the interaction term of ethnic by init years. In other words, does the effect on ethnicity change, or well, does the effect on over across and knit years, does it depend on which ethnicity you are? Then we'll look at some statistics. We'll choose to look at the regression parameter. Actually, we don't really need that. We would want to do this if we had chosen a covariate. It doesn't really add that much when we have just categorical variables. We will, however, choose to look at descriptive statistics. And continue. And we want to compute the means. We want the overall main effect for ethnicity and knit years, and we want to have means for the interaction. Now, our LSD test here only compares main effects of ethnicity and knit years. It doesn't do the interaction automatically. There's another step we could take to do that. Perhaps we'll do that later. So that's pretty much it. Let's see what we get. Okay, we have, it gave us the descriptive statistics for each subject. So that's probably more than we really need. Let's go to the type 3 effects, tests of fixed effects. And here, what is missing in this table that you had in your other table are sums of squares and mean squares. And we don't get that in maximum likelihood estimation. The way that the model is fit is different. It doesn't use those least squares formulas. It is an iterative process, and we'll talk about that later. Here is our covariance estimate. Now, on the CS diagonal offset, it's important to remember this is equivalent. And if the sample sizes were all equal and everything was equal and number of subjects in each group was equal and everything was equal, this number right here would be the same as the mean square error term in the least squares analysis of variance. And just as in that one, the square root of this will give us an estimate of the average standard deviation, which we can use as a denominator in computing effect size. Remember that. Repeated measures, CS diagonal offset, square root of this number, average standard deviation. So here we can see the various ethnicities and how refractive error changed. It was significantly different overall. We see that Asians are different from everybody. African Americans are different from Asians, but not Hispanic and Caucasian, and so forth. These are the years. You can see that we're a high plus, and we go down, 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 as years go on and myopia develops. And then it does a pairwise comparison of all the years. And you can see that it's looking at basically changes. Actually, let's look at this table a little bit more carefully. Here we look at year 7, minus 7 years before the onset, plus 6. And it's different for that year. So you would expect it to be different from all the rest of the years. On this next one, 6 is not actually different from 5. And it's not even different from 4. Here 5 is, you want to check it against 4. That is significantly different, so it's going to be different from all the rest. 4 is different from 3, so it's going to be different from all the rest. So except for at the top, at the very beginning, at high negative years, the amount of refractive error change is significant from year to year, overall collapsed across all ethnicities. Now let's go down and look at the two-way table of estimates. And this is the years, ethnic by years before and after. This is the table really you want to copy and paste into Excel so you can make a graph. This is the money page for your output. So let's copy this. Let's go to Excel. Let's paste it. Paste. Now let's draw a graph. We'll do it based on the years, and let's do a insert a scatter. Actually, let's insert a scatter with a line. And then we'll get rid of this chart title. Let's go in, right click, select data, and move this over here. We're going to edit series 1, call it Asian. Go down to add African American. The x-axis is -6.5. This is the y value, the series y values. Be right here. And through the magic of video editing, we add the other 4 lines, plus we go into design mode for our graph, added a chart element for legends. And then I'd like to just show you what to do to get these lines where they belong on the X and Y axis. You could leave it like this, but most people would not choose to do that. So let's take our init years axis right here, and let's do some options. And first thing that we want to do, in order to change where the x-axis goes, we have to say the vertical axis. Actually, it's not where the x-axis goes, it's where the vertical axis goes. We're going to have it cross at -8. So that we move that line over there. And let's also have the increment for init years be by year. I think we have room for that. Doesn't look too bad. Okay, let's make that a 1. Please stay there. Thank you. There we get initial years across here. Now we don't like that being there, so let's go to our y-axis. And the horizontal axis crosses at, we want it to cross down here at -5. So now we have something that looks a little better, although we do kind of miss this 0, and we could add in a vertical line there, or a horizontal line at 0. We could draw it in, or we could add a fifth line, but we're not going to do that right now. So you can see in our SPSS output, up in our type 3 fixed effects, we had a significant ethnic, we had a significant initial years, or years relative to myopia onset, and we had a significant interaction. So what does that mean in terms of our graph? Well, when you have an interaction, you don't between ethnicity and initial years, you probably would not talk too much about the ethnic main effect, because as you can see, the blue line, which is Asians, is higher at the beginning and lower at the end. So that's what makes the interaction significant, this cross, this lack of parallelness of these lines. And clearly the main effect of init years, even without respect to the interaction, its refractive error is going down over time. And the main effect is if you averaged all of these ethnicities and looked at the shape, it would go down. There would be, if you averaged across all the years, Asians would be a little poorer, but because they're up here, and really these probably aren't highly different, but that's what we have. So that is basically the technique for repeated measures in proc mixed.